In sub-exercise C of exercise 2, we are asked to find a second best efficient allocation in this economy. And this is a little bit different than the first best allocation because in the second best solution, the government is unable to observe individuals' income generating abilities. Okay, so this productivity parameter that we had before, this A, is not observable by the government anymore, but the government can only observe the income. And as you will see, this will lead to a situation where the first best kind of allocation is not feasible anymore. Yeah, and this is what we will be doing in exercise number C, sub-exercise number C. So let me give you an example on why the first best solution does not work in a situation where the government cannot observe the income generating abilities. So for this, keep in mind that the first best allocation was given. So if you ignore taxes for a second that we derived in sub exercise B, let's just assume there are no taxes for now. So the first best allocation was given by this year. So somebody with a high type, so high type individuals would receive 1.75 minus G as consumption, and they would provide 2 units of labor. Oh no, it's not 2 units of labor, sorry. They would generate 2 units of income. Low income, low ability types would consume 1 minus G, and they would provide or create 1/2 units of income. So now the following question, why? So why doesn't the government ask individuals about their type? Okay, so why doesn't the government just go to each individual and ask him, what are your income generating abilities? And then if high, so if answer is high, then the government would offer the following tuple, xh star and yh star. And if the answer is low, then the government simply offers xl star and yl star. Okay, so ignoring taxes here. So why doesn't the government just do this? So the government goes to each individual, asks the individual about his type, and then depending on the answer, offers him either the high tuple or the low tuple. So clearly there is an issue with this because if the government would simply do this, there might be misreporting happening. And to see why actually in this model that we're considering here, misreporting will actually happen, let's consider the following situation. So let's consider that the high type is really telling the truth. So he's telling that my income generating abilities are high. So then if high type, reports high, his utility is, what is his utility? So his utility is, just 1 second. So his utility is his consumption minus his income by the power of 2 divided by 4. So his utility would then be 1.75 minus G minus, so this should be a G, not a 6, minus, what was his, so it's 2 by the power, so it's 1, so it's basically 1, yeah? And this is equivalent to 0.75 minus G. Okay, this is utility. Now, if high type reports low, so he can do this because the government cannot really observe what his abilities are. So he can do this simply by lying. So his utility is then given by, so what was it? It was 1 minus G minus, then it's 1/2 1/2 by the power of 2 divided by 2, I think. So it's 1/4, so it's 1/8, I think, if I'm not mistaken. Oh no, it's sorry, it's 1/16 even, yeah. And this is roughly 0.94 minus G. And clearly, this here is higher than what we have here. So for an individual who actually has a high type and is asked about his ability, it makes much more sense for him to lie and just say that, yeah, his ability is actually low because his utility, which you have here, is higher in this case. Yep. So you can now see that clearly this reporting, like this voluntary reporting, will lead to a kind of distortion in the economy in that some types will lie. And now the question is, can the government do something in order to avoid distortions? That is to say that actually the types truthfully report what, like each of the types truthfully report what the type actually is. And this is basically a feature of the second best solution. Okay, so to avoid this problem, the government needs to introduce additional constraints. So the from a technical perspective, we will be using tools from mechanism design, if you're familiar with this, or the tools from moral hazard problems or models. So what we will make sure is that whatever solution we get, each of the types has no incentive to lie and to behave according to the type, actually. So this is what we'll be formalizing now. And it will be quite similar to what we have been doing in the exercise before. The challenge of this exercise is to simplify the optimization problem until the first order conditions are actually very easy to solve. Yeah. So this is the main challenge of this sub exercise. So yeah, let's go. Okay, what do we need to do? So the government faces the following problem. So the government wants to maximize So the government maximizes over XL, XH, YL, and YH. And it's maximizing social welfare, so the fraction of low types times the kind of social utility or the utility that the government derives from the low types plus the fraction of high types times the utility that the government derives from high types. Okay, so the next constraint, the first constraint that we will have is a budget balancing constraint that we have seen before. So 1/3 times YL plus 2/3 times YH should be equal to 1/3 times XL plus 2/3 times XH plus G. So this is a budget balancing constraint. Now, if you look at this, this is actually, so if you look at this problem, this is equivalent to the problem that we had in the first best allocation situation. Yeah. So this was the situation that we had back then. Now, in order to avoid this misreporting problem that I told you, that I described before, we need two additional constraints. So I will write down the constraints first, and then I will explain them. And I will also need some notation here with respect to the equations. So this budget balancing constraint, I will simply call it R. Okay. So whenever I refer to, so capital R, whenever I refer to this budget balancing constraint, I will just write R as a shortcut. The first additional constraint that we need is the following. So it's XH minus YH by the power of 2 divided by 4 should be weakly larger than XL minus YL by the power of 2 divided by 4. The second constraint is XL minus YL by the power of 2 should be larger than XH minus YH by the power of 2. The first condition that we have here, I will call this ICH, and the second constraint is ICL. And those are incentive compatibility constraints. So they make sure that each of the types has no incentive to lie. Okay, and how does this, how do those conditions make sure that it's actually guaranteed in equilibrium? So if you take a close look on ICH, this condition here is what? So this is the utility of the high type when he is getting kind of the high allocation. Okay, so when he's picking or choosing the high allocation. The right hand side is the utility of the high type when he's picking the low allocation. Okay, so the low bundle. Now, this constraint makes sure that in any solution that we find for this problem, the utility of a high type when actually choosing the high bundle is weakly larger than when he's choosing the low bundle. So this is eliminating the incentive for the high type to lie. Okay, so we will circumvent this problem that we had before in the beginning. The second constraint is basically the same for the low type. So the left-hand side is the utility of the low type when picking the low bundle, and the right-hand side is the utility of the low type when picking the high bundle. And if this inequality here is fulfilled, then also the low type will actually not have an incentive to lie. And what we will be doing now is actually solving this optimization problem by first simplifying it, because we have inequalities here as constraints, and this will complicate things a little bit. So what we will be doing is, we will simplify the incentive compatibility constraints. That's what we will be doing now. So as a first step, so let me write this here. So first goal or first step, simplify constraints. Okay, this is what we will be doing now. So first, note that ICL, so the incentive compatibility constraint for the lower type, can be replaced by a simpler condition. So let's suppose the following. So suppose the incentive compatibility constraint for the high type, so IC, holds with equality. Okay. What we then have is xh minus yh by the power of 2 divided by 4 is equal to xl minus yl by the power of 2 divided by 4. Now, adding and subtracting yl by the power of 2 to the right-hand side will give us the following. And if we rearrange, what do we have then? Then we have xh minus yh by the power of 2 divided by 4 minus 3/4 yl by the power of 2 is equal to xl minus yl by the power of 2. Okay, so why did we do this? Now consider the following. If we plug in the left-hand side of this expression here into the expression for xl minus yl by the power of 2 into the ICL constraint, we have the following. So let me write this down, plug in the left-hand side, so the red circle here, into xl minus yl2 by the power of 2 in ICL. What do we have then? Then we have xh minus yh by the power of 2 divided by 4 minus 3/4 yl by the power of 2 should be equivalent, or should be weakly larger than xh minus yh by the power of 2. Okay, and this is equivalent to, if you rearrange this, this is equivalent to yh being weakly larger than yl. Okay, so the crucial point here is that if the ICH constraint, so the incentive compatibility constraint for the high type, holds with equality, and if this condition here is fulfilled, then ICL, so the kind of incentive compatibility constraint for the load type is also fulfilled and we can ignore it. And this condition here, so YH being larger than YL, is much, much easier than the condition that we had before for YCL. Okay, so let me write this down. So therefore, if ICH holds with equality and I will give this inequality here, the simpler one, I will call this ICL prime. So this will be ICL prime, just to distinguish it from the ICL condition that we had before. So if ICH holds with equality and ICL prime holds, then ICL is fulfilled. Okay, so we can ignore it. So we can use ICL prime instead of ICL. Okay. Now, what do we have then? Then we have a simpler optimization problem. Optimization problem. Let me just copy from there. Some of the parts will be repeated. It's actually, so what you saw just right now, what I did, it's actually a nice tool if one of you is teaching online. Like this is GoodNotes I'm using, and you can basically kind of cut out something that you wrote on your tablet and then insert it somewhere else. So you save a lot of time when you need to copy things over and over again. So that's actually a quite useful tool because I will need it now. So the simpler optimization problem will now look the following way. So the ICH constraint now that we had before is the equality now. Okay. And the ICL constraint will be substituted by the more simpler ICL prime constraint, which is simply YH being weakly larger than YL. Okay. So this is this is a simpler optimization problem because we basically substituted one of the constraints to like one of the inequalities to a weaker, or like not a weaker, but a simpler inequality. And we made sure that one of the inequalities now is actually a equality. Yeah, so this is the ICH constraint. Okay, and yeah, of course, since the ICH constraint now holds with equality, we will also change it to ICH prime, okay? Just to distinguish it from the situation before. Good. There is one more thing that we need. So in order to get a explicit solution, so in order to get an explicit solution, so not a implicit equation defining a solution, but actually a number, like a value, we need the following. So in order to get an explicit solution, we need two additional constraints. So we will need two additional constraints, which make sure that both types actually choose a strictly positive amount of labor. Okay, we need to make sure that actually in what we offer the individuals, that they actually will choose at the end a strictly positive amount of labor, so they will generate a strictly positive amount of income, because otherwise the whole economy will break down. And those constraints are called participation constraints. So we need participation constraints. Okay. So what do we need then? So we need to make sure that both of them will actually choose a strictly positive amount of working time. So what we now will introduce is some kind of a notation for the utility of an outside option. So denote capital U bar is the utility of outside option. Which we'll call not working. So not working and not consuming, basically. Yeah. So just saying or just denying both of the bundles that the government could offer to an individual. So the condition that we will introduce, the two conditions that we will introduce now, will make sure that actually both of them will rather choose one of the bundles than not working at all. So the first condition is XH, so the utility of the high type when picking the high bundle should be weakly larger than UH. Okay, this is all that we need. This will be called the PCH, so participation constraint H. So the high type chooses rather a bundle of high types which is offered to him than not working, yeah, and getting his outside utility. The same for the low type, so XL minus YL by the power of 2 being weakly larger than UH. This is the participation constraint for the low type. Now, what can be actually easily shown now, so you see we introduced two additional constraints which will blow up the problem, but actually what can be easily shown is that if the participation constraint for the low type holds, and it holds that the high type has no incentive to lie, so this would be ICH here. So if this holds, then the participation constraint for the high type is fulfilled. Okay, the reason is quite simple. So if the low type has an incentive to how do you say it? If the low type has an incentive to participate, and the high type has no incentive to lie and to pick the bundle for high types, then this implies that the high type also has an incentive to participate, because the utility that the high type will receive when picking the low bundle is always higher than the utility that the low type will get, because the low type has higher costs. Okay, so if PCL holds, with equality and YCH prime is fulfilled, PCH will be fulfilled. And therefore, we do not need to consider this for the further analysis. Okay, so optimization problem now. So the optimization problem now is given by the following. Let me just copy again. Let me just adjust some of the things here. So nothing will change there. Shift this a little bit more to the other things because I need some space here. Okay, so good. So we have now the original conditions that we had before, and in addition, we will have now only the participation constraint for the low type, which will hold with equality. So XL minus YL by the power of 2 should be equal to UH. Okay, and this is the participation constraint. Sorry, let me rewrite this. This is the participation constraint for the low type, and to distinguish it from what I introduced on the page before, I will call this PC prime L. Okay, so this is kind of the this is like the most simplest optimization problem, most simple optimization problem, where we simplified the constraints to a in a nice way. So we only have either equalities as constraints, or we have inequalities which are very easy to verify here. Yeah, so YH larger than YL. This is IC prime L. This is the only condition where we just still have a inequality, but this is very easy to verify that it's fulfilled. But we can actually do one more thing. We can further simplify this optimization problem by substituting for some of the endogenous variables in the objective function here. So what we can basically do is we can use our constraints now in order to express XH and XL, so the consumption of the low type and the consumption of the high type, as functions of YL and YH. Okay. And what we will use for this is we will rewrite ICH prime and PCL prime. Okay, because in both situations we can rewrite and substitute the expressions in a way to get XL and XH as functions of YL, YH, and U prime. So use IC use ICH prime and PC L prime to express XH and YH, XL as functions of YL and YH. Okay, this will give us the following. This will give us XL is equal to UH plus YL by the power of 2 and xh being equal to UH plus YH by the power of 2 divided by 4 plus 3/4 YL by the power of 2. And now substituting these expressions into the objective function. So if you substitute those expressions into the objective function, you basically make sure that when you solve the optimization problem, those conditions are fulfilled, whatever solution you get. So substituting these expressions into the objective function will give us, will yield the following optimization problem. So now it's really simple. So now you have the following. Let me just copy again. No, I won't copy everything. So I need those two constraints here. So I need this and one more constraint, which is then just YH. Sorry, no, this is wrong. This is wrong here. Let me just rewrite everything by hand. So of course I need to substitute for the values. So I don't just copy it, but of course I need to substitute. And also you don't maximize over all the variables, but since you substituted for XL and XH, you don't, you ignore them and you only maximize with respect to YL and YH. And the new objective function, so if you substitute everything and you simplify, is given by 1/3 times psi at U bar plus 2/3 times psi U bar plus 3/4 times YL by the power of 2. Okay, this is the new objective function because we substituted for XL and XH and we simplified. Then what will be also a little bit changed is of course the budget constraint, because we also there we substitute for XL and XH. So the budget constraint looks in the following way, so such that 1/3 times YL plus 2/3 times YH is equal to U upper bar plus 1/6 times YH squared plus 5/6 times YL squared plus G. So this is, I will call this the R prime budget constraint. So the new budget constraint here that we have will be substituted. And the last condition or constraint is YH being weakly larger than YL. And this is ICL prime. And yes, this is so you see we took a lot of time to simplify, but this is actually an optimization problem which is solvable in a very easy way. Okay, so this pins down the solutions to the first order conditions, and yes, you will see that we can now basically solve this in a very short time because we simplified it a lot. So what we will be doing now is, so since there is still an inequality here, but this inequality is very easy to verify, what we will do is we will ignore ICL prime. So we will act as if ICL prime here is fulfilled. So we will ignore this. So we will derive a solution ignoring this condition, but then we will show that actually our solution verifies or is fulfills this condition ICL prime. This is what we will be doing. Okay, so writing this condition, so this optimization problem here, as an optimization problem in Lagrangian form is what we will be doing next. So the second step is solve the simplified optimization problem. This is what we will be doing now. So if you translate the most simple optimization problem that I showed you before into Lagrangian form, what you have is the following. You have the following optimization problem: max over YL, YH, and lambda. You maximize the Lagrangian, which depends on YL, X, sorry, not X. So YL, YH, and lambda. This is then equal to 1/3 times psi u bar plus 2/3 times psi u bar plus 3/4 YL by the power of 2 plus lambda, and then you basically use the constraint, the budget constraint R prime. So this is 1/3 times YL plus 2/3 times YH minus U upper bar minus 1/6 times YH by the power of 2 minus 5/6 by the power, no, 5/6 times YL by the power of 2 minus G. Okay, so this is the optimization problem in Lagrangian form. This can be solved quite easily. So first order conditions. The first order conditions are given by the following. So let us first consider the derivative of the Lagrangian with respect to YL. So the derivative of the Lagrangian with respect to YL is given by YL times psi prime U upper bar plus 3/4 times YL by the power of 2 plus lambda times 1/3 minus 5/3 times YL. This should be equal to 0. I hope you can still see this here. Yeah, it should be possible. The second condition, so the derivative of the Lagrangian with respect to YH is then equal to, this is much simpler. So lambda times 2/3 minus 1/3 times YH. This should be equal to 0. This is then simply equivalent to YH star. So I will, I denoted the first best allocation by star, and I will also denote the second best solution now by star. So don't get confused. This is now sub exercise C. So YH star is now the solution of the second best in the second best sense. So YH star is equal to 2. Actually, it's the same as in the first best, but the optimal or the second best consumption levels will be different than the first best consumption levels. Yeah, so keep this in mind. The last derivative that we need to consider is the derivative with respect to the Lagrangian parameter. So then we basically make sure that the budget is actually balanced. Okay, so 1/3 times YL plus 2/3 times YH minus U upper bar minus 1/6 times YH squared minus 5/6 times YL squared. minus g. This should be equal to 0. Okay, so those are the first order conditions. We will also numerate. Let me just put this in a nicer way here. So we'll also, no, it's not working. Sorry, 1 second. Yes, so we will also numerate those equations just to that you know what I'm referring to. So the first derivative, so the first order condition is equation number 1. The second one is equation number 2. And then we have equation number 3. Okay. So what we will be doing now is, solve this optimization problem, or solve this first order condition, this system of equations. So the first thing that we will be doing is we will plug in YH star in the second first order condition for YH in the third first order condition. Okay, so this is the first thing that we will do. So plug in YH star in 2 for YH in 3 and solve for YL. This will give you the following: YL star is equal to 1/5 plus square root of 30 times 0.7 minus U upper bar minus G upper bar, not G upper bar, minus G divided by 5. Okay, so what I said before was partially wrong. So the low ability types will generate different income than than what they would do in a first best allocation. Only for the high ability type, actually, the income generated is the same. Now, if you remember, what we now have is basically the solution of this of the second best allocation, but we only have the values for the income which is generated. So now we need to derive the second best consumption levels. So plug YH star and YL star back into the following relationships that we derived before. So into XL being equal to U upper bar plus YL by the power of 2 and XH being equal to U upper bar plus YH by the power of 2 divided by 4 plus 3/4 times YL by the power of 2. Yes. Those are the expressions that we derived when we further simplified the optimization problem to get rid of XL and XH. So if you plug in the values for the optimal income levels into those expressions, you end up with the following. So XL star will be equal to U upper bar plus 1/5 plus square root of 30 times 0.7 minus U upper bar minus G, the whole thing divided by 5. And then you take the square root of the whole expression here, and then XH star is equal to 1 plus U upper bar plus 3/4 times Yeah, actually, it will be the same expression as above. Yeah. So times this expression here. Just 1 second. Let me verify my solutions. Yes. This should be gone. And then, yes, that's the solution. Okay, yes. So those are the two solutions that we have. So with respect to consumption levels, so the consumption of the low type and the consumption of the high type. Therefore, just to summarize everything, what we then have is the second best allocation. So second best allocation is, yeah, the following. Let me just copy the values here. Oh, sorry, this didn't work out. Okay. So yeah, we have the two consumption levels, and then we have YH star being equal to 2, and YL is given by this expression here. Okay, somehow it does not work out. Let me try it again. Yes, now it's fine. Okay, so this is the second best allocation, and what you can now show is that, so this is what we derived. So this solution fulfills all the constraints that we have, but there was one constraint which we assumed to be fulfilled, but we still need to verify that it's true. So it was that YH is larger than YL, and actually you can show that this is indeed the case as long as so not as long as, but for YL to be like a valid solution, obviously plus G must be smaller than 0.7, because otherwise this expression here under the root will become negative, and hence we will not have a real solution, but we will assume that it holds. But now if you plug in for the values where we have valid solutions, you will see that indeed YH will actually be strictly larger than YL, and hence also the constraint with respect to the incentive compatibility of the low type will be fulfilled. So yeah, the solution is actually making sure that nobody lies. So each type will actually behave according to this type, and each type will actually participate. So they will actually not choose to not work, but they will provide a strictly positive amount of labor in the second best allocation. And we can actually do the last sub exercise, which is sub exercise D, real quick in addition to this video. So we are asked here to simply find the second best taxes in this economy. This is actually quite simple. So the budget is balanced and everything here is fulfilled. So the constraints are fulfilled. So the second best taxes, so this is sub exercise D, the second best taxes are given by, yeah, this is, you just need to plug in. So TH star is equal to YH star minus XH star, and TL star is equal to YL star minus XL star. Okay, so now plugging in those values is a little bit oversized here, so I will need much more pages for this. But this is actually the solution for the second best taxes. So it's basically the income generated in the second best allocation for a particular type minus the consumption of the of the particular type. Okay, and there will be a gap between those values. So this here will be strictly positive as it will be the same here for the low type, and those will be the second best taxes in this economy. And yeah, this was the last step exercise. So if you have any questions, please let me know. I will upload, as I said, like or have written in Moodle, I will upload those videos on YouTube. Probably I will also upload PDF solutions of that I used for the videos here. So if you if you do not like my handwriting, you can simply use the PDFs. But there is one slight difference in the PDFs that I will provide, in that the numeration of the equations that I'm using might be slightly different than the numeration that I'm using here. But actually, from the context, if you see them, it should be clear to which equation in the PDF refers to which equation in my videos here. Okay. So yes, then write me an email if you have further questions, or if you have suggestions for how to kind of write down things here on the tablet. So I'm doing like this style of exercises for the first time. Last year I did voiceover records on the solutions, and this is the first time that I'm using a tablet. So if you have any suggestions for me to improve the exercises when I'm writing down things, please let me know. I'm always open to improvements. And yes, then see you next week.